this video, we will be talking about order statistics. Let's go ahead and jump in. We'll start by defining an order statistic. Really what these order statistics are telling us is about the ordered values of the data. So specifically, we'll focus on how to find the distribution of the minimum and how to find the distribution of a maximum, given a sample of data. So starting with a bit of notation, let y1 through yn be independent continuous random variables with CDF capital F of y and PDF little f of y. The ordered random variables will be denoted a little bit differently. Down in the subscript, as you can see, they'll have a parentheses. So y sub parentheses 1 is the minimum, y sub parentheses n is the maximum. Within that, we could actually observe any of these possible order statistics. We could look at the distribution of the second smallest observation, etc. With these order statistics, these are placed in order. So they're not in, say, the order that we would observe them, but think of sorting observations from smallest to largest. So again, here, y sub 1 parentheses, this really just represents the minimum, or as a notation we can use for the minimum. Y sub n represents the maximum. So these are the two most common order statistics that we'll run across. Now, we can actually find the PDF for these order statistics using the method of distribution functions. So let's step through how we might find a PDF in general for the maximum of a sample, y sub n. So the maximum is the largest of all of the other observations. So what that means is that every other yi, by necessity, must be less than or equal to the maximum, yn. So the probability that the maximum is less than or equal to some value y is actually the probability that all observations are less than or equal to that value y. Because we're taking a sample of data, we are assuming that our observations are independent. So to find this probability that all observations are less than or equal to y, we can just take the product of the individual probabilities that the yi's are less than or equal to some value little y. This becomes then the product of the CDFs. So the CDF of the maximum is actually the CDF of each individual observation raised to the nth power. So now that we have that CDF, we can actually just take the PDF or take the derivative to get the PDF. So the PDF of the maximum here, f sub n in parentheses, again to denote the maximum of y. After taking the derivative and applying the chain rule, we get n times capital F of y raised to the n minus 1 power times little f of y. And that is how we get the distribution of the maximum. The minimum follows a very similar train of thought. The key idea here being that if the minimum is less than some value, say y, all other observations must be greater than the minimum. So we again start with trying to find the CDF of the minimum. That it really becomes 1 minus the probability that the first observation is greater than y, second observation is greater than y, and so on. So we're looking for a cutoff for all values other than the minimum itself here. Assuming independence, we then multiply our joint PDFs, so we get 1 minus the product of the probability that y sub I is greater than some value little y, which is 1 minus the product of 1 minus the CDF. So we get something like this for the CDF of the minimum. Again, because we want to find the PDF of the minimum, we'll take the derivative, apply the chain rule, and here we go. We get n times 1 minus the CDF raised to the n minus 1 power times the PDF. So now we have a form that we can use to find the distribution of the minimum. So our strategy here is going to be for a sample of data, figure out what distribution the desired order statistic, say the minimum or the maximum, looks like. A lot of the time it will turn out that this actually follows a distribution that we already know. So we can use similar arguments to find the distribution of the other order statistics. I've chosen not to really emphasize them in this video because primarily we're interested in the minimum or the maximum. Another order statistic that we do sometimes care about is the median, but most of the time the minimum and the maximum, let me go back, will give you the most information or the most useful information about a sample. So electronic components of a certain type have a length of life y with probability density given here. So we have 1 over 100 times e raised to the negative y over 100 power for y greater than 0. In other words, we have an exponential distribution here. So suppose that two such components operate independently and in series. So what that means is that when component 1 fails, the system fails. When component 2 fails, the system fails. So only one of them has to break down. We would like to find the density function for x, the length of life of the system. Well, it turns out that the length of life of the system is really the minimum time to failure, because when one part fails, the whole system breaks down. So we're looking for the distribution of y1. So our distribution of the minimum is n times 1 minus the CDF raised to the n minus 1 power times the PDF. Here we have an exponential distribution, so we can go ahead and use the CDF because we're already familiar with it. We also know that we have a system with just two components, so I'll plug in 2 for n. After a little bit of simplification, we get this. The distribution of the minimum is 2 over 100 times e raised to the negative 2y over 100. Now, you may recognize this as a distribution that we already know. This, in fact, is an exponential distribution. So as it turns out, the minimum of exponential random variables is itself an exponential distribution. Now, let's take a look at this from a slightly different perspective. Let's say that these components are operating in parallel. So if one component breaks down, that's okay, because we still have the second one to fall back on. So now our length of life really becomes the distribution of the maximum. So how long it takes the maximum part to break down. So here we'll find the distribution of yn by taking n raised to the CDF of y, or n times the CDF of y, raised to the n minus 1 power times f of y. Again, plugging in the CDF because we are familiar with it from the exponential distribution, we get something that looks like this. Now, unfortunately, the CDF of the maximum is not one of the named distributions. So the maximum of exponential distributions does not itself follow an exponential distribution, just the minimum. In fact, if we look at some simulated data, so here you're seeing some data from simulated random samples. There are 1,000 simulated random samples here, 2 components. What you're seeing on the left is the histogram of the minimum. This does look like a traditional exponential. It follows that sort of decay shape. The maximum looks a little bit different. It looks maybe like a chi-square or a gamma. It's not. It does sort of have a similar kind of chi-square shape, but unfortunately it's not one of those named distributions that we know. So if we wanted to do something like find the expected length of life of the maximum, so find the expected value of the maximum, the variance of the maximum, we would need to do that by hand. So that's it for order statistics. In the next set of videos, we'll switch to some other results related to taking samples from a population. I'll see you then.